Hello everyone! I made this video to provide you with feedback for the last case study that we did, and it was on taxafolin inhibition of carbonic anhydrase and acetylcholinesterase. And the data presented in this case were from a published paper a while ago. All right, so let's talk about what we learned in this case. There we go. So in the first question, the investigators measured the activity of carbonic anhydrase type 1 in the presence of increasing concentrations of taxafolin, and they provided a figure that was like the one I showed you. I plotted it myself in figure 66.7, and you should use this to determine the IC50 value, which is the concentration of inhibitor required to inhibit the enzyme activity by 50%. So you just do this graphically. This is activity plotted on the y-axis and taxafolin concentration in nanomolar on the x-axis. And if you just draw a line over from 50% and drop a line down, you should get the IC50. The values that you get here are a little bit different. Again, these are values that I plotted on my own, and I didn't have the raw data, so they might not have been exact. But the values plotted here, reported here, are the ones that the authors reported in their paper. So as long as you just got something close, that was fine. So here they report 27.7 nanomolar as the IC50 for carbonic anhydrase 1. Next, what they did is they measured the activity in the presence and in the absence of the inhibitor, and they measured the velocity in enzyme units per milliliter, and they used the artificial substrate paranitrophenyl acetate. So as described in the background, paranitrophenyl acetate has this structure here. It is colorless when carbonic anhydrase is able to, along with its other physiological mechanism where it takes water and CO2 to convert that to carbonic acid, and then that dissociates to form a proton and bicarbonate. It also has this capability where it can catalyze the hydrolysis of paranitrophenyl acetate. And when it does that, it releases acetate. It does the hydrolysis of this acetyl group right here. And then paranitrophenol is the product, and the paranitrophenol is yellow. So the substrate is colorless, and the water is obviously colorless, and acetate is colorless too. So what they did is they were just able to spectroscopically monitor how much paranitrophenol was generated per unit time, and you just have to measure how yellow it gets over a period of time. So you measure the lambda max at 348 nanometers, and then just use Beer's law to convert absorbance to concentration. So this is an artificial substrate. Again, the actual carbonic anhydrase substrates are carbon dioxide and water. So when they plotted their data, if you plot a Lineweaver-Burke plot, we plot reciprocal velocities. That would be the milliliters per enzyme unit over reciprocal substrate concentrations. That would be reciprocal millimolar with and without taxafolin. You should get a Lineweaver-Burke plot that looks like this. And that is characteristic of non-competitive inhibition that we talked about in class. And that means the inhibitor can bind to the enzyme or the enzyme substrate complex. And the substrate can also bind. So what that implies is that the inhibitor is binding not to the active site, but somewhere else. And this figure doesn't show this, but the idea is that there has to be some way that the active site is deformed so that the reaction can't occur, even when the substrate is bound. And all of these are all reversible, and all of these associations of the substrate and the inhibitor are non-covalent. Okay, so we talked about this in class. So this is the kind of Lineweaver-Burke plot that you get. This shows increasing concentrations of inhibitor. I just gave you one concentration of inhibitor. The Michaelis-Menten curve, which we did not plot for this case where the Km value in the presence and in the absence of inhibitor is the same, gives you a Michaelis-Menten plot looks like this. So we went over this in class. So if you look at this black curve right here, if you take the Vmax as the asymptote, and this isn't drawn very well, but if you take 1/2 Vmax and drop a line down, you get the Km with the inhibitor shown in pink, and that has a lower Vmax. So again, you take half of that Vmax, drop a line down, and you get the same Km. So Km normally in non-competitive inhibition changes, well, I mean, it does here too, by alpha and alpha primed, but since alpha and alpha primed are the same, we see that those cancel and the Km is the same. We can sometimes look at Km as a measure of affinity. Sometimes that can be a little tricky. Sometimes Km is a direct measure of affinity for some simple cases. Sometimes it's more complicated than that. You can always rely on the definition of Km. Km is that substrate concentration at which the velocity equals half maximal velocity. And I think from the Michaelis-Menten plot here, you can see that that substrate concentration is the same. And it's the same because the inhibitor, with the inhibitor, the Vmax is decreased. So anyway, alpha equals alpha prime. That makes our calculations a little easier. This also tells us the inhibitor binds to the enzyme and the enzyme substrate complex with equal affinity. If it had a preference for one or the other, alpha and alpha prime would not be equivalent. So for Vmax, we calculate that by just taking the reciprocal of the y-intercept. So without inhibitor, we get 0.70 enzyme units per milliliter. We get something a little smaller than that for the inhibitor, 0.3275. We can round that to maybe 0.33 enzyme units per milliliter. With Km, Km is the same, Km without the inhibitor and Km apparent with the inhibitor. And again, if we calculate the x-intercepts within experimental error, these are the same, 2.24 or 2.25 millimolar. So what we should note is if we look at our manual and we look at the table that I gave you, we can tell by inspection of the graph that this is a non-competitive inhibition. And again, the x-intercept will change by both alpha and alpha primed, but if they are the same, these values cancel. And that means our x-intercept doesn't change. But our y-intercept does. It changes by the factor of alpha. And since this is complicated, we have alpha primed and alpha. You could do alpha prime first, then do alpha, but it's just easier to do the slope. So what I do here is once I have identified what inhibition I have, I just look at this row and then I just don't look at the other ones. So this tells me how I can get alpha primed by either comparing the y-intercepts or comparing the Vmaxes, which is how I do it, or comparing the slopes to get alpha. So for Ki and Ki primed, you first have to calculate alpha and alpha primed. I did it both ways just to convince myself that I would get the right answer, but you didn't have to do that. You could have just compared the Vmax with and without inhibitor and noticed that the Vmax decreases by a factor of 2.14, and that's our alpha primed. Alpha would be comparison of the slope, and again, with an experimental error, you get the same thing. So what that means then, if alpha is equal to alpha primed, then Ki is equal to Ki primed. And if I put in the concentration of the inhibitor provided to me by the authors, I get a Ki equals Ki primed of 29 nanomolar. So again, what I want these values for is that, remember, Ki describes the affinity of the inhibitor for the free enzyme. So the inhibitor can bind to the enzyme. And after that, the substrate can bind if this is a non-competitive inhibitor, because the way we've described non-competitive inhibitors is they bind somewhere else, not at the active site. Ki primed is going to describe the affinity of the inhibitor for the enzyme substrate complex. But since they're the same, that means that the affinities are the same, that the affinity of the inhibitor for the enzyme and the affinity for the inhibitor for the enzyme substrate complex are the same. So you were asked to write a paragraph to explain what kind of inhibition that you think that it was and how do you know. So it's non-competitive based on inspection of the graph. That means that the taxophone doesn't structurally resemble the substrate, and you should note, I gave you the structure. It doesn't look anything at all like CO2 or water or paranitrophenyl acetate for that matter. And it can bind, as I showed you, by either the enzyme or the enzyme substrate complex, and it has no preference because the Km values are the same with and without the inhibitor. Using the definition of Km, the amount of substrate it takes to reach half maximal velocity is the same with or without the inhibitor. So I'm confident I can make that kind of statement. With the affinities, I'm not as confident, so I wanted to make some statements I'm confident about. Ki and Ki prime values are the same with an experimental error, and they indicate the affinities of the inhibitor for the enzyme and the enzyme substrate complex, respectively, so the affinities are the same. The Vmax goes down. You can't achieve maximal velocity even if you have lots and lots of substrate. So because, again, for non-competitive inhibitors, at least the way we've described them in class, if the inhibitor doesn't bind to the active site, that means substrate can be bound. But even though the substrate is bound, the substrate can't be converted to product as long as the inhibitor is still there. The only way you get from substrate to product is if you happen to have the inhibitor dissociate, and then if the substrate is the substrate is bound exclusively to the enzyme and there's no inhibitor there, then you can get to product. But if the inhibitor is there, you can't. So the Vmax goes down. All right, we have 2 more inhibitors, so the answers are going to be similar. So the IC50 value, again, for carbonic anhydrase 2 is a little bit different. The authors report 43.3 nanomolar. We can plot a similar curve with the data that I gave you that they provided. And again, we also get the by inspection. This is non-competitive inhibition and the same kind where the alpha equals alpha primed. So we get slightly different values though, so we have to calculate Km and Vmax. We do it the same way. So Vmax is calculated with and without inhibitor by taking the reciprocal of the y-intercept. Km is determined the same way by taking the negative reciprocal of the x-intercept, and here within experimental error we get the same value. And to calculate Ki and Ki primed, I do the same thing. I compared the slopes for alpha, and I compared the Vmax without and with inhibitor, and I just wanted to convince myself with this to get the same value, and I do. So if alpha is equal to alpha primed, I can use alpha to solve for Ki, and I could solve for alpha prime, but it's the same. So I get alpha equals alpha primed, Ki equals Ki primed, and I get 22.9 nanomolar. So what I did for this slide is I copied everything that I just showed you, and I just put carbonic anhydrase 2 instead of carbonic anhydrase 1. So since we get the same appearance on our plot, we can say all of the same things about this inhibitor, the taxofolin inhibitor for this enzyme as we could for carbonic anhydrase 1. The values we get are slightly different, but in terms of how it behaves as a non-competitive inhibitor, we can say the same thing. So I just copied the slide and put carbonic anhydrase 2 here, so you might notice it's exactly the same. Okay, so if I compare these, then I made a little table for myself. I looked at the IC50 values and I looked at the Vmax. So the Vmax is slightly higher for the carbonic anhydrase. So, and I did ask you about the non-inhibited reaction. So substrates converted to product at a greater rate for carbonic anhydrase 2 than carbonic anhydrase 1 because we measure the Vmax and it's greater. Okay, how about acetylcholinesterase? We can do the IC50 there. The authors report 30.1 nanomolar. And they also provide us with enzyme data and enzyme units. Although here we use a different reaction. Again, this is an artificial substrate. The actual substrate for acetylcholinesterase is acetylcholine, and it catalyzes hydrolysis into choline and acetate. So this is similar. This is not acetylcholine. This is a thiocholine iodide salt here. But the acetylcholinesterase will hydrolyze that. It's similar enough to give us thiocholine and acetate. All of these are all colorless, so this isn't going to help us. But if we throw in some DTNB into our assay mix as well, then what happens is a reaction occurs where we release this moiety right here of the DTNP. So there's a reaction that occurs and produces this thionitrobenzoate, and that is a yellow compound. So here we can monitor the reaction spectroscopically. So again, artificial substrate, but it lets us have some way of knowing how speedy the reaction is. So again, we get the same kind of appearance. We have a non-competitive inhibitor here too. So different enzyme, different substrate, but we still have non-competitive inhibition. So same thing. For Vmax, we take the reciprocal of the y-intercept with and without the inhibitor, and I have these values right here that I've reported. Same thing with Km, and I calculated the x-intercept to convince myself I would get the same Km, and I do. And I did the same thing with Ki and Ki prime. So I calculated alpha prime by comparing the Vmax values. With an experimental error, I get the same thing. So alpha equals alpha primed, Ki equals Ki primed, and I get 18.1 nanomolar for my my values. Here again, I just copied and pasted, and I put in acetylcholinesterase. So again, this behaves exactly the same way as the other two. So everything that we said about the non-competitive inhibition of carbonic anhydrase 1 and carbonic anhydrase 2 applies here as well. So I made myself a nice summary table. The other thing that I did just to help me with the subsequent questions is I added some of the other information that I gave you in some questions. So I have my enzyme and my inhibitor, and I don't have all the information here, just what was even in the paper. So these three enzymes are all inhibited by taxophilin in a non-competitive way according to the Km and the Vmax values that I obtained. These are the IC50 values, and here are the Vmax values without inhibitor, with inhibitor. And I can note that Km equals Km apparent, so I just have one entry right here. And the Ki and Ki primed were the same, so I also have just one entry here. And then I just put these here just so that when I answer the next questions, I have some nice visual to look at. Okay, so the next question doesn't have the right answer, and it doesn't have the right answer because I don't know the answer to it, and I did a little bit of research, and I'm still actually a little confused about it, if truth be told. So the authors report in their paper that the way that taxophilin works is that, let me go ahead and in my case study right here. The way that it works is that they describe it as the phenolic compounds like taxophilin, and there are lots of others besides taxophilin, that they coordinate and displace the water hydroxide bound to the zinc ion. So if that's what they said, is this consistent with the data? On the face of it, the answer is no, it isn't. Because if that's really how it works, if they really are correct about this, the water and the hydroxide are bound to the zinc on it. That's the active site, and that's characteristic of a competitive inhibitor, not a non-competitive inhibitor. A competitive inhibitor, if we'd gone through all the kinetic data, oops, I forgot my subscripts here. I have to go back and fix that. The competitive inhibitors would show an increase in Km and no change in Vmax, whereas here we see an unchanged Km and a decreased Vmax. So kinetically, that's not what we get. So there are a number of ways to answer the question, and that's one of them. You could just say, no, that's not consistent. If this really is how it works, then these are the changes in Km and Vmax we would expect that are characteristic of a competitive inhibitor, and that isn't what we see. Well, what if we take this description sort of in maybe an expanded way? Maybe, and it's not to say that the data are wrong, and I've seen other phenolic compounds, and they seem to be in the literature, not that I've done an exhaustive search, but they do seem to give the same kind of Landweaver-Burke plots that we got here. Maybe the taxophilin has a second binding site. Maybe this is behaving as a non-competitive inhibitor, but we'll say non-classically. Maybe the taxophilin does bind to the active site. It binds to the enzyme at the active site. Non-competitive inhibitors classically don't do that, but maybe that's what happens. And maybe taxophilin has a second binding site that does actually bind somewhere else, and maybe that does somehow impact what's happening on the active site. If that's how it works, then our data would be consistent. But maybe what happens is that when the taxophilin binds to the other site, maybe that displacement does occur, but it somehow happens indirectly. I don't really know. I tried to find out, and I couldn't find out. In any case, taxophilin doesn't appear to behave classically, in that it doesn't behave like the textbooks say it's supposed to behave. If it really is competitive, you wouldn't see these Km and Vmax changes that we saw. If it is non-competitive, then it doesn't do this directly. So the way that this question was graded is, what did you come up with, and did you support your answer? So your grade on this question was based on not how you answer the question in terms of did you support this or don't you, but how did you support it? So that's interesting. So I wanted to sort of expand on that question by looking at what's going on in the active site. And again, I gave you this picture. This is the zinc, and these are the 3 histidines that's coordinated to. There's a glue and a 3 residue nearby. That's the bicarbonate. And again, it's the enzymes crystallized at the bicarbonate because that would be inhibitory. In the active enzyme, that's occupied by a hydroxide ion, and that's shown here, where this is IMA for imidazole, and that's the zinc. And if this is the OH minus, which is here at the active site, the first step is the OH minus. Well, that's not really the first step. The first step is that proton relay we described in class that produces this OH minus ion to begin with. And then this nucleophilically attacks the carbon dioxide. We bring in our water as our second substrate. That regenerates the enzyme and also produces the carbonic H2CO3, the carbonic acid products, which really we can think of this as a dissociated bicarbonate and proton. I was looking for mechanisms, information about the mechanisms, and I found this little video right here. So I wanted to show that to you. So I'm going to hit start animation, and you can slow this down. That's the slowest it'll go. It goes through the steps. So up here, and it's on a loop, so we'll wait for it to start back to the beginning. So 4, 5, and 6. It'll start back. Okay, so step 1 is, wait for it, this step 6. Okay, so step 1 is, it's coming. Step 1 is return to start. So step 1 is we have the water, the proton relay that produces the hydroxide. Here comes the CO2, nucleophilically attacked by the hydroxide. We produce the bicarbonate, and then the bicarbonate dissociates, and then we have that proton relay again, and then that regenerates the enzyme, and then that histidine actually rotates out. So that's sort of the end of the mechanism. So again, if that's really how this works, that's the active site. And I'll go back to my PowerPoint here. If that's really how it works, and if the phenolic compounds really do displace that OH minus, they really are acting at the active site. So I find this a little puzzling, but that's science. Maybe we can do some more experiments and figure out what's actually going on here. Okay, so I asked you to compare taxophilin and acetazolamide, and I gave you IC50 values and Ki values. So you would have to, the way that you would answer this question is you'd have to describe what IC50 values are, and they're given as the concentration of an inhibitor required to emit the enzyme activity by 50%. So low values means it takes less. The Ki values indicates binding higher binding affinity. So I made myself a little table right here. So if you look at the acetazolamide, the IC50 for both enzymes is higher than it is for taxophilin, and the Ki values are also higher. So here we can see that the acetazolamide, it takes a higher concentration of acetazolamide to give you 50% inhibition, and we also see that the affinity of the acetazolamide for both enzymes is a lot lower. Question 10 asks something similar, except IC50 values were all that the authors provided. So again, if you look at the IC50 values, then compare the one that's given with the one that you obtained from the graph that was given. Again, it looks like it takes more enzyme to inhibit the enzyme activity for 50%. So maybe that's a better inhibitor. But a lot of you pointed this out, which is very good. Is it a better drug? Maybe, maybe not. If we just look at the ability of the inhibitor to bind to the enzyme and to inhibit its activity, we might think, yes, that's a good thing. This is where you start. But remember, we're in a lab with test tubes. What happens biochemically and physiologically when you give this drug to the patient? So I try to do a little bit of research here, and it turns out that taxophilin has lots and lots of other biochemical and physiological effects. So this isn't the only marker of whether this is a good inhibitor or not. So that's important to point that out, especially for all of you who are interested in careers in healthcare. This is the reference where I got all of these data for the case study. I hope that you find this case study to be an enjoyable investigation. And if you have any questions, I'd be happy to meet with you and your team. Thank you very much for your attention.